Great, thank you. So I'm going to talk about the ShadowCam instrument on the Korea Pathfinder Lunar Orbiter, our KPLO, and we're focusing on Faustini PSR for this talk and showing what ShadowCam coupled with some of the other LRO data sets is showing us about this interesting PSR. For those of you not familiar with the instrument, ShadowCam is an optical camera with a lot of heritage from LROC and NAC, if you're familiar with the LROC camera, but it is about 200 times more sensitive. So it's designed specifically to image in very low light conditions in the PSRs where you only have scattered light available for illumination. And so you can see the large baffle here for also improved stray light rejection. So we get a pixel scale of about 1.7 meters within the PSRs, but it can only image in indirect illumination. So anything that's directly illuminated saturates. And so the idea then is the PSRs do get scattered light from surrounding terrain that is illuminated, and that light scatters into the interior. And then we're able to use that diffuse light to image the interior of many of these craters. So Faustini is one of the large PSRs. It's one of the sometimes referred to as the three amigos. There's three large craters near the pole. It's the third largest PSR, and we've now collected over 150 images within Faustini. So KPLO has finished its primary one-year mission. We're now in an extended mission, so we've been there for about a year and a half. And so we've been able to observe a full season. And so we arrived right around peak southern hemisphere summer. And so we had optimal lighting conditions in the south to image. And we're now back in southern summer again. So we're able to get a full season of images. And so the illumination conditions vary a lot between seasons, and I'll show some examples of that later. So this is a mosaic here I put together with some of those early images. There's about a dozen or so images here. So these were during peak summer. So this is when we had really good lighting conditions. So the floor of Faustini, so I'm highlighting the floor, and all these figures, the pole is on the left side of these images, so that's the poleward side. And so in general, the floor appears to be sloped poleward. And so you generally have this upper area that is sloped downward, and then it flattens out around a central mound. So you have this sort of flatter area with a mound, which is probably a remnant, maybe a central peak. And then it drops down into these lower areas, which are very flat, and it turns out also very rough. And so we can sort of define these three different levels based on these contours here. They sort of conform nicely to surface roughness. So here I'm trying to be a little more quantitative what I mean by surface roughness. So I've taken the latest Barker et al. DEMS of the South Pole and generated some roughness maps using what's called a vector ruggedness measure, which essentially quantifies the dispersion of surface normals within a moving window. So it captures variations in slope and azimuth in a single metric, and does a pretty nice job at separating slope from roughness compared to, say, like TRI, which is commonly used, which correlates with slope. This one decouples slope nicely. And what you see is around these contours, the roughness seems to correlate well with these boundaries. And I've passed it through a mean filter just to make it a little more easy to see that this central area around the mound is much more smooth, and also this upper area. And then I did this for 3 different length scales and put this into an RGB figure just so you can see where it's sort of bluer here, it's rougher at shorter length scales. So we can define these morphologic units just for the sake of discussion. So I'm just going to refer to upper, middle, and lower unit just based on their elevation here. And then we also see a few double PSRs that are sizable. These are areas that are shadowed from that initial reflected light. So they require multiple bounces for photons to get in there. So these are very low illumination areas. They're also very, very cold. And if I have time, I'll talk a little bit more about those. We also see some interesting irregular depressions, possibly a remnant lobate scarp here that's separating this lower unit. You can see that here. So it would be about a 4-kilometer lobate scarp. Here's some of those irregular shaped depressions. It's not clear what's forming them, but you've got, I don't know if they're related to impact craters or not, but you've got some deflation of the surface. And we see these in a lot of the PSRs. And so focusing on that, on this boundary here, around the central mound between this lower and middle unit here, there's a clear difference in the crater population. So a lot of what's driving these differences in surface roughness appears to be differences in the retention of craters. So when we look at the size frequency distribution, there's quite a difference. So in this lower unit, which is really rough, we can see the craters are near saturation, and then below sort of about 40 meters, they deviate from that curve. So something's wiping out those smaller craters. And then on this middle unit, you can see that we're not near the saturation curve at all. It's actually closer to a sort of production function of about 100 million years. So the retention of craters is very different between these two units. We also see things like elephant hide terrain, sometimes referred to as tree bark texture. We see that on above this contour, but not below. And so this does seem to suggest that the mobility of regolith is different between these two units. So you've either had diffusion of terrain, and the creep of the terrain is perhaps different. And so that might explain why the crater retention is different. So this is that RGB image of roughness. I'm zooming out now. So here's Faustini PSR, there's the rim. And we see a lot of linear alignments of roughness, which are crater rays. So I've outlined a couple here. These are most likely from Tycho based on the orientation, possibly another set from perhaps Jackson. We also see some areas of elevated roughness along the walls. I think this was highlighted on Tuesday as being radar bright here. And when we look at ShadowCam over here, we can see that you have this pitted texture. So it looks like maybe a debris field of maybe secondaries. And so these are actually aligned with Shackleton. So it's possible Shackleton did project some debris at low angle, hit the rim, and then struck the other side here. So this is the site of one of the Artemis 3 candidate sites, Faustini Rim A, I believe it's called, which would suggest that if we did go there, there'd be material from Shackleton in that site. Okay, so we see boulders on the floor. They're always associated with impact features. And not surprising, the more the fresher the appearance of the crater, the more boulders we see. So all the boulders seem to be being excavated from depth. There are many rimless craters that are very degraded that have no boulders. So here I've mapped them out and then just colored them by the number of boulders associated with each crater, just to look at the distribution. And they do correlate really well with radar. So this is from Caleb Fassett's latest release data on the mini RF. And you can see everywhere where we see boulders, we see bright CPR. And so that would imply that all the bright returns we're seeing, at least in Faustini, are related to these boulders. But we see that's not a random distribution. The lower rough unit has many more rocky bouldery craters. So that seems to suggest that whatever substrate that is sourcing these boulders is maybe at a shallower depth, and that the upper unit represents a thicker material that has to be excavated. And that seems to be supported by another observation where we think maybe there's some buried sizable impact craters. So here I'm focusing on the upper unit. I've detrended the topography, and that brings out some subtle features that look like perhaps these are some buried kilometer-sized craters here. So again, suggesting that upper unit's a thicker deposited material. I'll talk a little bit now about the thermal environment. So what I'm showing here are thermal model results. So we modeled the temperatures throughout the whole KPLO primary mission. And this shows how the seasonality really influences the amount of light that gets in there. So largely what's driving the scattered light into the PSR is how much of this wall that's facing the equator gets illuminated. So this is showing peak temperatures during the primary mission during the summer. And so you can see that almost that entire wall gets illuminated during noon. It goes almost all the way down to the floor. And then as we go into winter, only the very top of that wall is now able to be illuminated. And so very little light gets scattered in. It gets really dark in the winter. It gets very cold. And so seasonality really drives a lot of the temperature variations. And you can see this here now. So this is again taking that model, but showing the average or the mean temperatures of the floor over time. So this is, we got into orbit right before summer solstice. And you see the really large diurnal variations as that wall gets lit up. And then at winter, you're barely lighting it up and there's very little variation in temperature. So it gets very cold. And then you can see that minimum temperatures continue to actually get lower. So there's some inertia in the system. So it does actually continue to get colder. So spring and fall temperatures are not identical. There is some inertia there. Thanks. All right. So this is showing diviner temperatures. Ben Greenhagen talked about diviner a bit. This is using the thermal channels from that to characterize the temperatures. So I'm showing the maximum and average temperatures. And so you can see there's this gradient. So this upper unit remains colder. And so that means that the sublimation rates of water are about 6 orders of magnitude lower in this area. But overall, this is a very cold PSR. So there should be cold trapping of water throughout the whole floor. But using some of the Rufu's latest results, you can map out how long the floor has been a PSR based on the obliquity history of the moon. And so that upper unit's been a PSR for much longer. So it's had a longer period of time to collect volatiles. And that thermal gradient has some interesting implications for other supervolatiles that are more volatile than water. And so we expect that there could be a gradient in deposition or at least retention of some other volatiles across the floor. So that upper unit is much more likely to be able to cold trap a variety of super volatiles. And this is showing the depth to stability for CO2. So as you go deeper in the regolith, the thermal wave amplitude gets smaller, and so the maximum temperatures are lower. And so in this upper region, CO2 is stable pretty close to the surface. So there's the potential for more cold trapping in that cold half. Here's one of those double PSRs. One of the more intriguing features we've seen is what's called a lobate rim crater. If you caught Mark Robinson's talk at LPSC, he talked a lot about this feature. It's got a really unusual morphology. It's also a double PSR, so the interior only gets light off of some of the surrounding terrain that's already diffuse light to begin with, so it's very cold. These are showing model temperatures from within that double PSR, and so we're predicting that it's consistently below 55 Kelvin, so this should be cold trapping CO2. So these double PSR should be really nice, should show a really nice history of volatile delivery to the moon. They should preserve all these super volatiles. So let me wrap up since I'm getting close to the end here. Elevation, slope towards the pole, roughness also increases towards the pole. So there's, a lot of this is driven by differences in crater degradation rate. So this seems to suggest that terrain diffusion and regolith migration is asymmetric across the floor. This seems to is somewhat correlated with temperature, and that temperatures are also asymmetric across the floor. The walls are also very different in their thermal profile. So the equator facing wall gets directly illuminated. It gets very hot, over 250 Kelvin. The poleward facing wall is within the PSR, and so it remains below 100 Kelvin. And so the wall itself is a cold trap for water. So you could have differences in temperature cycling and volatile retention driving a lot of this asymmetry. Or it may have nothing to do with temperatures. It's possible Amundsen, ejected material onto half the crater and just created an asymmetry in material properties. And with that,
Thank you so much. Yes, we can have one very short question. Oh, okay.
Hi, Barbara Cohen, Nessa Goddard. This is really nice work. I'm intrigued by your ancient possible craters and their age relationship to the Faustini cold trap itself. Can we use the presence or absence of what we don't see in ShadowCam? They probably didn't excavate, or if anything in the subsurface that's volatile, or if they did, it was a long time ago because we don't see bright ejecta from those ancient craters. Is that right? Can we tell anything about age relationships that way?
I have to think about it. Yeah, we don't see a lot of bright craters. So, I think we can use that to constrain amounts of water, possibly. I know Schweiley he's working on this very much. I think you have to have pretty high levels of water to see a really obvious reflectance change. As far as tying that into, you're talking about the obliquity history and the age. Like, do we see a difference of where? the
Yeah,
oldest
and it
PSRs
tells you about
are?
the supply too, when the supply came in.
Yeah,
right?
yeah, that's an interesting point. I haven't
Interesting.
looked more closely at that, but it might be interesting because we've been focusing on PSR versus non-PSR, but to keep in mind that the PSRs weren't always that size is something to fold into this analysis, for sure.
Thanks.
Yeah.